Hello, dear listener. Welcome, my friend. As the day gently fades, and the quiet stillness of the evening begins to envelop us, let us embark on a tranquil journey together. A journey not through bustling streets or distant lands, but through the profound, quiet corridors of thought. A journey into the very fabric of our universe, and how we understand it. Tonight we will explore the serene and intricate realm of the philosophy of physics. Imagine, if you will, a vast cosmic tapestry, woven with threads of light and shadow, of motion and stillness, of existence itself. The philosophy of physics is the gentle art of examining these threads, not just to admire their beauty, but to understand their nature, their origin, and their meaning. It's a discipline that seeks to illuminate the deepest conceptual and interpretational issues that arise from our scientific understanding of the physical world. It's where the rigorous equations of physics meet the boundless wonder of human inquiry, a place where science and philosophy embrace, hand in hand. For centuries, thinkers have gazed at the stars, felt the passage of time, and pondered the very stuff of which everything is made. Historically, philosophers of physics have delved into monumental questions. What is the true nature of space itself? What is time, this relentless river that carries us forward? What constitutes matter, the tangible reality around us? And what about the fundamental laws that orchestrate their magnificent dance? These are not mere scientific questions, but profound philosophical ones, touching upon the very essence of being, of knowing, and of reality. This discipline, as we explore it tonight, draws its gentle wisdom from many springs. It draws from metaphysics, which asks about the nature of reality itself, from epistemology, which ponders how we can truly know anything, and from the broader philosophy of science, which examines the very methods and foundations of scientific inquiry. And crucially, it remains ever open, ever receptive, to the latest, most breathtaking developments in both theoretical and experimental physics, allowing our understanding to evolve, to deepen, and to grow more beautiful with each passing discovery. Now, as we settle deeper into this peaceful exploration, let us turn our attention to the great, luminous pillars upon which modern physics stands, three magnificent structures that each present their own unique and captivating philosophical landscapes. First, let us gently consider the world of quantum mechanics. Quantum mechanics, a realm where reality itself seems to shimmer and dance with possibility, a realm often described as strange, even counterintuitive, yet profoundly beautiful. Here, the philosophy of physics grapples with truly mind-bending questions. What, truly, is the nature of a quantum state? Is it a description of reality itself, or merely a description of our knowledge of reality? We ponder the famous measurement problem, the perplexing question of how the nebulous possibilities of the quantum world seem to collapse into a definite reality when we observe them. What is the role of the observer in this cosmic drama? Does consciousness play a part, or is observation simply any interaction? These are not questions easily answered, but they invite us to contemplate the very boundary between what is observed and what is real. Imagine, for a moment, two tiny particles, separated by vast distances, yet intimately linked, their fates intertwined in a phenomenon known as entanglement. If you measure a property of one, the other instantaneously reacts, no matter how far apart they are. This non-locality, as it's called, challenges our classical notions of cause and effect, and asks us to reconsider the very nature of interconnectedness in the universe. And then there is the profound relationship between the quantum world of the very small and the classical world of our everyday experience. See, how do the fuzzy, probabilistic rules of the quantum realm give rise to the solid, predictable reality we perceive? The answers are not simple, dear listener, but the contemplation itself is deeply enriching, inviting us to release our rigid assumptions about how the world must be. Next, let us drift into the elegant landscape of relativity. Here, we encounter the profound insights of Albert Einstein, which transformed our understanding of space and time forever. The philosophy of physics carefully examines the conceptual foundations of both special and general relativity. No longer are space and time seen as separate, immutable backdrops against which events unfold. Instead, they are woven together into a single, dynamic fabric called space-time. Consider, for a moment, the concept of simultaneity. In our everyday lives, we assume that now is the same for everyone everywhere. But relativity teaches us that simultaneity is relative, dependent on one's frame of reference. What is now for you, moving through space, might be a different now for someone else in a different state of motion. This profound realization challenges our intuitive grasp of time and space, inviting us to expand our minds beyond the confines of our immediate experience. We ponder the nature of causality, the chain of cause and effect, and determinism within this flexible space-time. Do events unfold in an inevitable sequence, or is there room for genuine contingency? Relativity also invites us to contemplate the very beginning of our universe. The redshift of distant galaxies, the echoes of the Big Bang, all point to a cosmos that began about 13.8 billion years ago. And with this, the concept of space-time itself perhaps emerging from a singularity. And what of the compatibility of relativity with quantum mechanics? These two magnificent theories, so successful in their own domains, seem to describe reality in fundamentally different ways. The search for a unified theory, a theory of quantum gravity, is one of the grandest challenges in modern physics, and it deeply engages philosophers in understanding its conceptual implications. The idea of a privileged present moment, so natural to our human experience, seems to dissolve under the gaze of relativity, suggesting that all moments in space-time are, in a sense, equally real, equally existing. What a thought to gently ponder as you drift towards sleep. Then, let us softly move to the third pillar, statistical mechanics. This field bridges the vast chasm between the microscopic world of atoms and molecules and the macroscopic world of our everyday experience. Philosophers here delve into the intricate relationship between these two scales. How do the chaotic, random movements of countless particles give rise to the smooth, predictable properties of gases, liquids, and solids? We explore the very interpretation of probability. When we say something is probable, are we speaking of an objective feature of the world, or merely expressing our own uncertainty due to incomplete information? This leads us to the profound mystery of the origin of irreversibility and the enigmatic arrow of time. Why does time seem to flow in only one direction, from past to future? Why do broken cups never spontaneously reassemble? The second law of thermodynamics, which states that entropy, or disorder, always increases in an isolated system, seems to hold the key to this. But what does this truly mean, philosophically, for our understanding of the universe's destiny? The foundations of thermodynamics, the very laws governing heat and energy, are deeply explored. And the role of information theory in understanding entropy, how our knowledge, or lack thereof, shapes our perception of disorder and order in the universe. These are questions that touch upon our very understanding of explanation and reduction in physics. Can all macroscopic phenomena be reduced to the behavior of their microscopy? See constituents, or do emergent properties arise that require new ways of understanding? It's a gentle reminder that the universe holds layers upon layers of understanding, each with its own beauty and its own quiet mysteries. Beyond these three great pillars, the philosophy of physics continues its gentle inquiry into other fascinating domains. We contemplate the profound nature of physical laws themselves. Are they immutable truths inscribed in the fabric of reality? Or are they mere human constructs, our best attempts to describe patterns we observe? We reflect on the elegant role of symmetries and conservation principles, those enduring quantities that remain constant amidst change. And we ponder the deep relationship between mathematics and the physical world. Is mathematics merely a tool for describing reality, or does it somehow underpin reality itself? As new frontiers of physics emerge, such as the quest for a theory of quantum gravity, the mind-bending possibilities of quantum information, or the intricate beauty of complex systems, philosophers are right there, offering their unique perspective. They gently argue that this deep conceptual analysis, this quiet contemplation of foundations, not only helps us interpret the implications of new theories but can also, in its own subtle way, guide the very development of future physics, helping us to ask better questions, to see beyond the immediate, and to explore the truly fundamental. Now let us turn our gaze to two of the most fundamental concepts that underpin all of physics, indeed, all of our experience, the very existence and nature of space and time. These are central topics in the philosophy of physics, inviting us to ponder whether space and time are truly fundamental, existing independently, or if they are emergent, arising from something deeper and more basic. And we also ask, how are space and time operationally different from one another? Let us begin with time. Time, that elusive, relentless river. In the classical mechanics of Isaac Newton, and indeed for most people up until the 20th century, time was considered a fundamental quantity. It was seen as an absolute, universal flow, ticking away uniformly for everyone, everywhere, independent of any observer or event. Imagine a grand cosmic clock, perfectly synchronized across the entire universe. This was the prevailing view. Time was a quantity that simply was, irreducible, a backdrop against which all phenomena unfolded. However, dear listener, the whispers of new theories are beginning to challenge even this fundamental assumption. Certain contemporary theories, such as loop quantum gravity, propose a truly radical idea that spacetime itself might be emergent. Imagine this, not a smooth, continuous backdrop, but a tapestry woven from discrete, fundamental loops, or quanta of space and time. As Carlo Rovelli, one of the founders of loop quantum gravity, beautifully puts it, no more fields on spacetime, just fields on fields. This profound idea suggests that time, as we experience it, might not be a fundamental given, but rather something that arises from the intricate interactions of more fundamental entities, much like the smoothness of a flowing river emerges from the countless individual water molecules. Operationally, time is defined through meticulous measurement. Our standard time interval, the conventional second, is precisely defined as 9,192,631,770 oscillations of a hyperfine transition in the 133 cesium atom. It's an incredibly precise definition, grounding this elusive concept in the observable, measurable reality of atomic behavior. And from this definition, from this incredibly stable atomic rhythm, the very nature of time, and how it interweaves with other fundamental quantities like space and mass, allows us to define concepts such as velocity, momentum, energy, and fields. But the most profound shift in our understanding of time came with Albert Einstein's theories of relativity, and Hermann Minkowski's concept of spacetime. They revealed that the rate at which time passes is not universal, but rather depends on one's relative motion and gravitational field. Imagine two clocks, perfectly synchronized. If one travels at very high speeds, or is in a stronger gravitational field, it will tick slower than the other. Time, then, is not the same for everyone everywhere. It is intimately linked with space, merged into a single, deformable entity, spacetime. Einstein's general relativity, along with the beautiful cosmic symphony of the redshift from receding distant galaxies, tells us a remarkable story, that our entire universe, and possibly spacetime itself, began about 13.8 billion years ago in that singular, explosive event we call the Big Bang. And within this relativistic framework, the very idea of a privileged present moment, the notion that there is something metaphysically special about now, compared to the past or future, becomes far less plausible. Because time is relative, because what is simultaneous for one observer is not for another, the idea of a universal, cosmic, now, that applies to everyone everywhere, seems to dissolve. All moments, past, present, and future, in a sense, simply are within the vast expanse of space-time. A deeply peaceful thought, allowing us to let go of the urgency of the present, and embrace the eternal. Now, let us turn our gentle attention to space. Like time, space is one of the few truly fundamental quantities in physics. It is so basic, so pervasive, that we cannot define it in terms of other, more fundamental known quantities. It simply is. And similar to time, our understanding of space is grounded in careful measurement. The standard unit of space, the meter, is precisely defined as the distance traveled by light in a vacuum during a time interval of 1/299,792/458 of a second. This definition beautifully links space to time and the universal constant of the speed of light, intertwining these fundamental concepts. In classical physics, space was conceived as a three-dimensional Euclidean space. Think of it as a vast, unchanging grid, where any position could be precisely described using three coordinates: up/down, left/right, forward/back. This was the familiar, intuitive space of our everyday experience, a fixed stage for the unfolding of events, parameterized by that steady, universal time. However, as we have gently explored, special and general relativity transformed this picture. Space and time are no longer separate. They are interwoven into a four-dimensional continuum, space-time. This means that a location is not just defined by its three spatial coordinates, but also by its temporal coordinate. Events occur at specific points in space-time. And the presence of mass and energy causes space-time to curve, like a bowling ball on a stretched rubber sheet, and this curvature is what we perceive as gravity. And, dear listener, the journey of understanding space continues to evolve. While we experience three spatial dimensions in our everyday lives, many speculative theories in contemporary physics propose the existence of even more spatial dimensions, perhaps tiny, curled-up dimensions that are imperceptible to us, or larger ones that we simply haven't yet detected. These ideas, while currently theoretical, open up entirely new landscapes for philosophical thought, inviting us to imagine realities far richer and more complex than our immediate senses can apprehend. What does it mean for reality to have hidden dimensions? How would such a universe feel? These are questions that can gently carry your mind to realms of quiet wonder. As we bring our tranquil exploration to a close for tonight, remember that the philosophy of physics is not about finding definitive, final answers. Rather, it is about asking ever deeper, ever more refined questions. It's about cultivating a sense of wonder, a profound appreciation are the mysteries that lie at the heart of existence, and the incredible journey of human understanding. As you drift towards sleep, may these thoughts of space, time, quantum mysteries, and cosmic elegance accompany you. May you find peace in the vastness of the universe, and in the beauty of humanity's ceaseless quest to understand it. Sleep deeply, my friend. May your dreams be as vast and serene as the cosmos itself. Good night.